All right, another morning. Last morning before the exam. All right, this is as good of a starting problem as any. Okay. Okay, so with a diagram to the right in mind, find the value of the hanging mass such that the current I3 is in equilibrium. None of the three currents have a significant mass. Gravity is present. I1 is in, I2 is out, are equal in magnitude. And held fixed by an external source, the crab. All the currents are parallel and infinitely long, except I3's length is given L. All the currents form a right isosceles triangle with D as a hypotenuse. Okay, good. So this is going to be D over 2. Oh, okay. I got it. So then that B, F, B, or no, B. So then, okay, I got it. So my, okay, so now we gotta find, okay, did I get it right? Mu zero I three I L over pi dg. Okay, good. Easy. The Diffeek one. All right, but let's get to this nasty one because this one I know is hard. Biot-Savart with a surface integral. It shouldn't be that hard, but I don't know. Whenever it, changes, it gets a little nerve-wracking. Referring to the diagram, using the Biot-Savart law, find the magnetic field magnitude along the y-axis, B of y, due to the spinning disk of charge. Note there's only charge present from R over 2 to R, and consider the charge density constant and given as sigma. Hint, the Biot-Savart law gives dB in terms of IDL. But in this problem, think of dB in terms of ILDI, dq over t, and I is the circumference of the arbitrary, or L is the circumference of an arbitrary ring of charge. Okay, so we have a disk here. This is R over 2. This is R. So we can call this I hat, J hat, K hat. Spinning omega. Oh, and this thing has total charge density sigma. Okay, so what we want to know is, let's just find the current in a little loop. Okay, so it's going to be sigma, so the Q sigma times 2 pi R dr. Okay, so we have the dq. Now omega t is equal to 2 pi, so t is equal to 2 pi over omega. And what we want is that di will be equal to dq over t, or delta q over t, which will be equal to, and this will be, di. So this will be sigma 2 pi r dr divided by 2 pi times omega. So the 2 pi cancels, and we are left with sigma omega r dr is di. And what we want to do is leave that unevaluated. So L, so now we want L di is equal to 2 pi r. All right, so we're adding back in that 2 pi r. So we're going to be, so L di is equal to 2 pi sigma omega r squared dr. And now we need cross r hat though. But what do you, for a ring, what is r hat? So hold on. B is equal to integral dB by the principle of superposition, which is equal to the integral of mu 0 over 4 pi times, and in this case, L di cross r vector over the norm of r cubed. Now we know what di is, but what is, and we we know what L is, so this can just go in here. What is the direction, though? The direction... Yeah, what is the direction of the current? Presumably it's just... But is that... I guess for a component, you're going to get this, like this. This is y, this is r. So this is going to be y squared plus r squared. That has to be... Oh, this is big R, this is big R, this is little r. Is it that? I don't know if it's that. But what direction? Okay, I gotta look at the answer. I do not understand what is going on here. Okay, alright. So hold on, that's a hint. So... Wait, actually, I gotta... He calls this theta. So wait, hold on. So if this is going in like this and then like this, then this is dB. So then this is dBy. And this is theta. So cos theta, dB cos theta is equal to dBy. So now we just need to add up the x component. So this is a little r. That's confusing. Um... I this r is a different r than this r, right? Yeah. This, what did he must have called this something r prime. That little mark there is not a mistake. Because Wait, but why is he able to do this? And why is he able to do this and say that the angle? Why is he able to say that they're perpendicular? Okay, let's just say, L of theta, the position on the thing is going to be little r cos 0, little r sine. Be right back. So yeah, I'm confused about this step. How come how come it's 90 degrees? So this is equal to Hello? What the hell? The background quite peaceful? Yes, it is. What is going on here, though? What the fuck is going on? Okay, actually, I do see it. I think I see it. Yeah, I see it. Okay, so in that case, what we're gonna do is we're gonna do. Okay, so it's actually not that bad. So this one is like, it's not a surface integral D. Well, it kind of is. It's hard. This one's hard. Do again. If I have time tonight, do it again. It's hard. It's hard because you have to. Okay. As was shown in the lecture, a spinning disk of charge has a magnetic moment. Okay, it's spinning omega b. I think this is the same problem. Okay, good. This is an opportunity to do it again. So the total charge is Q. This radius is R. Let the circular disk have a radius R and total charge Q. Be spinning with an... Here he gives no hints, so you really got to figure this out. So U0 QW over 2 pi r squared. From 0 to r, A. Oh, he did A too. I didn't even see that, but I did A as well because it's confusing because if you do a little r, then you have two different r's and it makes it really confusing. What's up, Beyond Lineals? What exam am I preparing for? I'm preparing for just a physics exam. Just a electricity and magnetism physics exam. All right, so this one is actually the same hard, same Oh, yeah, I like this one. I like this one. Do again, hardest circuit problem. Hardest circuit problem, was it really? Okay, so what do you do to solve this? So first, this is 0. But the thing is, there's going to be charge on these capacitors. Now the charge here and the charge here have to be the same. And this is just a property of capacitors in series because this conductor initially started with 0 net charge. So even though there's charge separation, there's still 0 net charge. So then all the charge here has to be minus all the other charge here. So then you get, C1 is equal to Q1 over V1. C2 is equal to Q2 over V2. So then Q1 is equal to C1 V1 and Q2 is equal to C2 V2. But then that means C1 V1 equals C2 V2. So then you can find that V1 is equal to C2 over C1 V2. Okay, so now we have that's the voltage across this in terms of these capacitances. And what do we want to find? We want to find this potential. Okay. Okay, so we see, A, B, C, D. So, see that, the voltage across B, across R2 is equal to that. So if we find, so the VR2, since no charge through the full caps is equal to I total times R2. So first we can find, so that's that VR2. So V minus 1 minus VR2 is equal to 0. This is going to be I. No, but we want to solve, actually, we want, Okay, good. All right, so that one's starting to make some more sense to me, but I did a little bit memorize it. But you know, you immediately see, okay, this is in parallel with this. Since these are full, then all of the current goes through here, so we can use V equals IR to derive the current through the circuit. Then we can use the, you know, the voltage divider thing to find the voltage across R2. Once we find the voltage across R2, we can set it equal to the drop across the both caps. Then we can find the voltage across one cap in terms of the voltage across the other cap, and we can then simplify to solve for the voltage here. Okay, not bad, not bad, not bad. Let's see. This one was weird, I think. Oh yeah, you just use Ohm's law twice. I never understood why he did it as hard as Okay, we got to get to the new stuff cuz look at all these problems that I have not looked at yet. How many is that? It doesn't tell me how many lines I've selected. Just tell me how many characters I've selected. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22. 22 problems left to go. And I'm not going to have as much time to stream. Okay, this one's easy. POS integral dB. He's probably going to ask a nasty integral dB. Just given how many are in the archives, it's likely. All right. Force of one loop on another. All right, actually, let me look at all of them and make a note about this. So this is going to be, F of I1 on I2. Okay, let's see. A charge Q and M given is injected into a solenoid of radius big R and length big L, where a uniform magnetic field exists. The charge will spiral through the solenoid in a helix along the x-axis matching the center of the solenoid's axis. The charge is initially ejected with a velocity that only has an x and y component, but the y component of the velocity is not given. Instead, you are given that the radius of the charge's circular motion is just inside the solenoid and therefore equal to R. Gravity is irrelevant. Find the initial vertical velocity to make this happen, and then find the number of rotations n that the charge will make before it exits the solenoid. Okay, so we have Q, M, solenoid, B. Okay, R is given. So we have wait. Okay. Q R B over M is equal to VY. Okay, so we found that. Now we want to find the number of helices. So number of equal to the time. Find the number of rotations that the charge will make before it exits the solenoid. This thing has length L. Okay. The helices is going to be the time to travel that distance. So it's going to be, you know, L is equal to Vx t. T is equal to L over Vx. So now we need to find t because it's the total time divided by the period time. And the period time is going to be, so we're going to get, you know, R. QBL over Vx 2 pi m. Easy, bro. Okay, this is actually easy helix. Okay, torque balance. This is the classic torque balance. Doesn't seem like it should be that hard. I'll figure it out. There's probably some nuance to it. There always is. No back. I forgot. I actually have to leave at noon, so I only have an hour and a... Oh, shoot. Okay, wait. I need to do something. I have to download some photos of my lab notebook. To make sure. Okay. Where's my lab notebook? Okay, I think it's this. Wait, actually, And I should be able to rotate them in the thing. Because this is worth 5% of the grade, so it's like, you know, if I lose one, and it's only out of 5 points. So if I lose 1 point on it, I lose a whole percent in the class. Okay. Okay, so I think I'm good on this. The thing is, the exam is worth like 30% of the grade, so I don't know. Okay. Oh, I can do this, right? Ah. Okay, so we're just gonna take a quick look at what happened this quarter in lab. Okay, it does look like it's in order. Logistics. Okay, so the resistor codes, the sig figs. Since this has 2 sig figs, then you got a round. Okay. Lab final definitely has analog VOM. Okay. All right, next. Measuring resistance. Okay, he wants to see the tolerance bounds and then where it lands. The analog VOM. I forget how the hell that thing works. Okay, this shouldn't be too bad. Ohm's law. I don't know how much data we're going to be taking, but here's some symbols. Okay. All right, basic stuff. Okay, DC circuits. We got, okay. Okay, parallel and series resistors. Okay, this is actually the part that's probably going to be on the lab final. Okay, so these are the attributes of a signal: trigger level, DC offset. Yeah, trigger level, period. Okay, good. Here's the thing that probably is going to be the hardest. Is yeah, this is kind of the thing. Is the root mean squared stuff. Was root mean squared on the back, or was this it? VRMS is equal to the integral from 0 to big T of V of t squared dt over t, and then all square rooted. Square root integral V of t, t0 to big T divided by t. Okay. Wait. I think that this is... Oh, yeah. Okay, that's right. Because the peak to peak is given on the oscilloscope. Okay. Then for a square wave, you're doing it over one period. Capital T is the period. We just kind of even did that homework, that exam problem. Wait. Let's see. Oh, yeah. Okay. All right. That one's pretty chill. And then the triangle one is kind of gnarly. I really hope the triangle one isn't given, dude. This integral was so stupid. How did we measure? Let's see, what equipment do we use in this lab? Where's my equipment? Okay, here we go. We use the function generator, the BK, and the DMM. I think that there's an RMS thing. Okay, I forget exactly. And then we have the discrepancy tests here. I always forget the order of this thing. No symmetry. Oh, yeah, I redid the derivation here. Yes. So nasty. VPP over 2 root 3. All right, finding capacitance. Okay, we drove an RC circuit with a square signal On lab final. This is on the lab final. Okay, so he's probably going to ask you, okay, find the T1 half and then find the capacitance. So you're not given the capacitance. Maybe you're given the resistor value. I mean, likely it's a comprehensive test. You round to 1 sig fig y. Oh, because of this? Okay. And then you round b. So if we're given a bunch of b's, we calculate the mean b, right? This is the standard deviation. So where did I write the final b? Okay, so then you need to do it like this. For lab final needed, give answer in millitesla. How to convert grams into newtons. I did this in Julia. I did this hella quickly, so. Anyways, the error bar thing is the standard deviation over the square root of the number of samples. Okay, all right, we did it. Let's go back to save. Okay, that's not like. Like, I don't know what to expect, but I really hope it's easy. I need a 5 on that thing. Lemon Leaf, bro. Man, my boy Lemon Leaf always in the chat. Okay, 56. Did we look at this? All right, torque balance. Let's do it. Okay. So let's call this I hat, J hat, K hat. The loop has mass. Refer to the diagram. There's gravity in this problem. A rectangular loop of current is hinged about one side. The loop itself is mass m loop. In addition, there's another mass mh hanging at the middle of the outside Okay. The loop is within a uniform magnetic field B directed in the I-hat direction. Oh, come on, dude. Okay, so we can't even use our coordinate system. We have to use his coordinate system. So I-hat. So if you're like this, you need to spin it like this. So K's still up, J's coming out. Oh, what did he do? I-hat. My thumb is I-hat. My index is J-hat. So he comes over here and then he flips it over. I-hat. No, what? I-hat. There we go. I-hat, J-hat, K-hat. Okay. What a nasty coordinate system. I'm gonna call this the origin. Okay, so we're gonna get. So wait, what is the actual problem now? Loop is within a uniform magnetic field to B directed in the I-hat direction. Find the current I such that the loop maintains its area in a horizontal plane. Okay, so tau equals I alpha. Cis is loop. Then this is 0, solve. Okay, so now we get tau m loop plus tau m plus, and this is really going to be, G loop. It's really tension loop plus tau, or this is going to be tension plus tau m loop or G loop plus tau b is equal to 0. Okay, so I'm gonna. Okay, so this point P is equal to. So first off, so now we're gonna get so R. So this thing is gonna make this. So K hat is pointing this way. I messed up the minus sign. Oh no, because J hat points down. Yes, this is minus LMG because this is gonna make it go like this and push down. So it's gonna rotate there. So that's the first one. That torque, the center of mass. Oh, dude, this is what killed me on the last exam is I couldn't remember it. So the center of mass is going to be L over 2. So now tau due to gravity. I'm pretty sure it's just, yeah, it's just going to be minus L over 2, 0, 0. And then the force applied is going to be Fg is equal to mg. So this is going to be mg. So this is going to be k hat minus k hat lmg over 2. Or lm loop. So this is, okay, so then minus k l m loop G over 2. Now we need the torque due to the magnetic field. So B is going this way, and we need the current. We're gonna need the current. Let's see if the current was going this way. So we need the current to go this way so that the force is up. So the current. So mu must be k hat and it's going to be, so L is equal to IA, which is equal to IWL, and then B, this is going to be k hat cross B I hat, so I J K. This is going to be 1. This is going to be 1. This is going to be J hat I L W B. Wait. No, 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 no. Hold on. No, no. Oh, this is minus J. This is minus J. Okay, this is minus J. Oh, wait. So this is 1, and this is minus 1. So this is going to be K hat. Yeah, this is going to be K hat. Okay, so we're going to get LMG minus LM loop G over 2. And this is minus. Right, so let's make these plus. Or, no, let's keep them minus. Over LWB is equal to I. Okay, let's see the answer. All right, nice. That's it. Yeah, that's what I got. Point mass M connected to it, to one end. The other end of the wire is connected to a pivot so that the mass could swing down like a pendulum if released. Say the wire and the point mass are held at rest in a horizontal position. After the point mass is released, find the induced EMF in the wire across its length when the mass and the... Find the induced EMF in the wire across its length when the mass in the wire at the bottommost position, but still moving. Okay. Okay, I don't understand those ones. I need to go back to those ones because those ones are so weird. Okay, consider the diagram. There exists a uniform magnetic field only in the boxed region. Outside the box region, a positive charge Q travels with a horizontal velocity to the right, a distance d below the horizontal boundary line. After the charge leaves the box region at the boundary line, its velocity now makes a 45-degree angle to the horizontal. Find the magnitude of the magnetic field in the boxed region that will make this happen. So the fact that it starts here doesn't mean anything, I believe, because there's only a B field here and there's no E field. So this thing is going to travel at constant velocity until here. And then let's see, it's going to be V cross. Do we know the direction? Well, it has to, the force has to be up. So V cross B, B is into the page. It's minus K hat. Let's see, this is a pi over 2. So at that stage, though, V would be V cross B. Wait. V cross B straight up. Is that right, though? I think that it shouldn't it be, if this were the radius of the circle, then this would have to be pointing straight up. So it's not. Are the dimensions of the square given? Oof, this is a really good one. Okay, so we're just going to spam looking at them for right now. So we're just going to look at them. So this is a really interesting B field. Yeah, I need to do this one. Basically, I'm just filtering out all the ones that I've definitely seen before. Okay, yeah, so this is just, what is it? Calculate the terminal velocity. Induced EMF terminal velocity. Actually, I should probably do again. Because it's likely that kind of problem will be on the exam, I feel like. Okay, a solid infinitely long straight wire of radius r carries a current I. There's a POS problem. Carries a current I that is uniformly distributed through its interior. Current density is uniform. Find the magnitude of the magnetic field inside the wire at distance r over 2 from the center. For a full credit, a full detailed explanation is required. All right, so he's doing the E out, B in thing or something. A charge Q of mass m and of unknown velocity enters a uniform magnetic field, B, and then exists as shown in the diagram. Find the time it takes to exit the field. Okay, so presumably of unknown velocity, but okay, well, it initially starts here. This is r. This is going to be t over 2. You find t, and then you do t over 2. Yeah, so it's normally 2 pi m over qb. Now this is just, okay, easy. Find the B field at the center of a spinning disk of charge. The disk has radius r. The charge is not distributed uniformly, but varies to. Ooh. Okay. I'll be right back. I gotta go to the bathroom. Well. Oh well. Well. All right, that's all I'm gonna get to do this morning. All right, well, it's, wait, let's look at the last of these. Come on. Okay, expanding loop, EMF thing. What is it? Find the induced current. An infinite length of straight line current is shaped into a circular loop whose plane has the origin. Find the magnetic field at the center of the loop. POS. Yeah. Okay. This is like this was a homework problem. B loop plus B wire POS homework problem. Ooh. Okay. I wanna do this. Find the value at the potential at point A. All right. This is kind of a subclass of problems that I really didn't see when these, just the way that the problems got shuffled up. I didn't see these. Okay. Which point are we finding? V of D. Or V of C. Um shit. Oh, caps of equal value. So this goes to 1. So this goes to -10. Okay, never mind. I got it, except I didn't see that these caps are of equal value. All right. Nice, we did it. We looked at all of them. I looked at 100 physics problems. And what did I learn? An inkling of how I might make a motor. And some really interesting stuff about solenoids. I think the solenoids are really interesting. Uniform B field. This is a series cap problem. Pretty standard at this point. Okay, that's it. I'm gonna get a bite to eat. Then I'm gonna crush this lab exam, and then I'm gonna study tonight, and I'm gonna get a freaking 100% on this physics test. We're gonna go through as many problems as I can. From I get out at 5, I'll get home at like 5:30, eat something. It'll be 6. I'll have hopefully 5 hours of solid more studying, and then tomorrow. The thing is, I have another exam tomorrow, and it's pretty important. I gotta study for this bio thing. God. I'll probably just look through. All right, I'm out of here.